Hi, today we are going to look at nomenclature of chemicals. But before we do that, if today is the first time you are watching this channel, I urge you to subscribe, like, share, and comment. Now let's look at the nomenclature of chemical compounds. When we talk about nomenclature, it's basically talking about naming. We want to look at how to name chemical compounds. We said we name chemical compounds using what we call the IUPAC nomenclature. IUPAC means International Union of Pure and Applied Chemistry. This union has come out with the various names for certain compounds. So when you are in Ghana, the name you give to NaCl would be the same name if you are around any part of the world. So today we want to look at how to name chemical compounds, and we'll be looking at the nomenclature of an ionic compound. We said under ionic compound, we'll be looking at under ionic compound, we'll be looking at the types of ionic compounds. We want to look at a simple cation, simple anions, and oxo-anions. When we talk about a simple cation, we said simple cations are basically ions that carry positive charges. So if you have an ion or a compound that is carrying a positive charge, it is referred to as a simple cation. There are rules in naming simple cations. We said, first of all, identify the element. So when it is written in its chemical symbol, you identify the element. So if I have Na, you should be able to tell what the Na stands for. When you are done identifying the element, you should be able to tell the oxidation state of the element. These oxidation states must be written in. There are rules in naming simple cations. First, you need to identify the name of the element. So if it is written Na, you should tell us what the Na is. After identifying the name of the element, the next thing is to identify the oxidation state of the element. The oxidation state of these elements are written in capital Roman numerals and in brackets, but these are written for only compounds that have variable oxidation state. When we talk about a compound with a variable oxidation state, it's a compound or an element that has more than one oxidation state. In an example like iron, we have iron existing in more than one state. So we have an ion 2 and an ion 3. So if we were asked to write the oxidation state of these ions, so if we were asked to write the name for this compound, you should tell us the state of the ion, because the compound has more than one state. So you have to let me know, or you have to let us know, which of the ions are you referring to? Are you referring to an ion 2 or you are referring to an ion 3? But if the compound does not have a variable oxidation state, we don't write their oxidation state in capital Roman numerals and in brackets. Now, we said note, there should be a space between the cation name and the word ion. So when you are done naming, you add the word ion after you've written out the oxidation state. We are saying that between the name of the cation and the word ion, there should be a space between them. Let's take some examples. If I have Fe2+, Fe3+, Cu2+, and Pb2+, the rule says that I should identify my element. So my Fe2+ stands for Fe is ion. Now the oxidation state of ion is the charge the ion is carrying. So ion is carrying a +2 charge. Ion is a variable element because we have ion 2 and ion 3. So I'm supposed to specify. So I'll write ion 2 ion. The next is ion 3. So I will say ion 3 ion. Cu2 plus, Cu is copper, and the copper carries an oxidation state of +2. So that will be a copper 2 ion, and so on. With those that carry fixed oxidation states like H plus, Na plus, Mg plus, etc. H plus, H stands for hydrogen. So we'll call this hydrogen ion. You don't have to tell us that it's hydrogen 1 ion, because hydrogen does not have a variable oxidation state. It only exists in one state, which is it carries an oxidation state of +1. So that is how we name simple cations. Let's go to simple anions. Simple anions are basically, when we talk about anions, these are negatively charged ions. So ions or elements that carry negative charges are called anions. How would we name an anion? You said to name an anion, you first of all need to also identify the name of the element. When you do that, the next thing is to take out either 2, 3, or more letters in the ending of the word, which is called the suffix. So you go to the suffix, you take out 2 or 3 or more letters in that word, and you replace it with the word IDE. Then you add the word ion. So for example, if I have a Br minus or S2 minus, Br stands for bromine. I am going to take out 2 letters. So I take out 2 or 3 letters from bromine, and it becomes a bromide, and I'll add the word ion, a bromide ion. The next is sulfur. So I'll take out 3 letters from sulfur, and I'll add the word IDE. It gives me a sulfide ion. So that is how we name simple anions. Now that we know how to name simple anions, let's try to now combine both the simple anions and the simple cations together to get what we call binary compounds. In a binary compound, we are saying that these are compounds that are made up of only 2 elements. So the chemical composition of the elements are just 2. So when you have 2 elements in a compound, we say such elements are called binary compounds. How do you name a binary compound? We said to name a binary compound, the first thing you need to do is to name the metal part first, because binary compounds are composed of a metal part and a non-metal part. The metal parts are our cations, the non-metal parts are our anions. So the cation part should be named first. Now when you name the metal part, you should check for the oxidation state of the metal. Is it a variable metal or it is not? If it is variable, you must write the oxidation state of that metal in brackets and in capital Roman numerals. Then when you are done, the next part is the non-metal. You name the non-metal part. You identify either 2 or 3 or more letters from the suffix, and you replace it with the word IDE. Now between the names, that is the cation name and the anion name, you leave a space. So let's take some examples. So I am having that name the following binary compounds: NaCl, MgO, LiH, CaF2, and Cl2 and Cl2. I am going to try out the first one. Now sodium, now the chemical compound is NaCl. Na becomes my metal part, so I will say Na is called sodium. Then I'll go to the non-metal part, which is my Cl. It is also called chlorine. I'll remove 2 letters from chlorine and it becomes a chloride. When you are done, you now sum up both or add up both the cation name and the anion name. But don't forget, we did not consider the oxidation state of the sodium because it is carrying an oxidation state of +1. So the name becomes sodium chloride. But note, the names should be written in small letters. So I don't know if this S looks like a capital letter to you. It should be in small letters. Sodium space chloride. If you do understand, try II to IV and leave your answer in the comment section. Let's go to the next one, which is oxo-anions. We said when we talk about an oxo-anion, they are basically negatively charged groups of atoms that contain oxygen. So a negatively charged atom that contains oxygen is called an oxo-anion. How do we name oxo-anions? We said 1. State the number of oxygen atoms using the word mono if the oxygen atoms is 1, di if they are 2, tri if they are 3, tetra if they are 4, penta if they are 5, and so on. After identifying the number of oxygen atoms, the next step is to look at the first part of the other element. The first part of the other element is named, and the suffix of the 2 or 3 letters is replaced with AT. This time we are not doing ID, we are replacing with AT. And so, example, if we have sulfur, it becomes sulfate. Manganese becomes manganate. And we now look for the oxidation state, which is we calculate for the oxidation state, and we write that in capital Roman numerals and in brackets. If you don't understand how oxidation states are being calculated, you can watch that video on how to calculate for oxidation state in one of my videos. After calculating for the oxidation state and putting it in brackets and in capital Roman numerals, we add the word ion to it. Let's try this example. So MnO4 minus and PO4 3 minus and CO3 2 minus. So we are going to try out the A. Now my number of oxygen atoms are 4. So I will say tetraoxo. The next element, or the first name of the element, is manganese. So I'm going to remove some letters from manganese and it becomes a manganate. Then I'll find out the oxidation state of my compound and I'll write that in capital Roman numerals and in brackets. Now note, here we calculate for the oxidation state. We don't assume if it is variable or not. You calculate for the oxidation state and then you put it in capital Roman numerals. So when we do that, we'll have Mn to have an oxidation state of +1. So our name becomes tetraoxo manganate 7 ion. The same thing applies to B. The number of oxygen atoms would be 3. So we will call this So we identify the number of oxygen atoms, and the number of oxygen atoms here is not 3B, it is rather 4. So we'll make that correction So we have 4. So 4 oxygen atoms, we will call it tetraoxo. Then the name of the other element is phosphorus. We will replace it. We will replace the suffix with 2. We will replace the suffix of 2 or more letters with the word ate, and that becomes a sulfate. We will calculate for the oxidation state of the P. We have P plus 4 minus 2, which is equal to -3. We'll end up having P to be plus 5. So the oxidation state of the compound is plus 5. So we'll call this trioxophosphate 5 ion. So you can try C and leave out your answer in the comment section. The last thing we want to look at is oxo-acids. We said for naming oxo-acids are basically acids containing oxygen atoms. So we call them oxo-acids. To name them, you first of all identify your oxo-anion in the compound using the steps you used earlier in identifying oxo-anions. And when you are done, you replace the word ion in your oxo-anions with the word acid. So let's take an example. I have HNO3A, H2SO4, and CH2CO3. These are all oxo-acids. How do we name them? For the first one, I will identify my number of oxygen atoms, or I will identify my oxo-anion, which is NO3 minus. So the name would be 3 oxygens will be trioxo. The next element is hydrogen, so we'll call it the next element is nitrogen, so we'll remove some letters and put ADE and put ATE. It becomes nitrate. Then, because it contains oxygen, we'll add a word. Because it contains oxygen, we'll add a word acid, which indicates it's an acid. The same thing applies to B. The number of oxygen atoms are 4, so we'll call it a tetraoxo. The next element is S, which is sulfur. We'll replace some of the letters with ATE. It becomes sulfate. We calculate the oxidation state. We have 6, so this is called tetraoxosulfate 6. And we'll remove the word ion and add the word acid. I believe this lesson was clear. If there is anything that you are still in doubt, you can leave your questions in the comment section. Hi, do you have difficulty when it comes to understanding quantum numbers? If yes, today we are going to look at quantum numbers. But before we do that, if today is the first time you are watching this channel, I urge you to subscribe, like, share, and comment. Let's look at quantum numbers. When we talk about quantum numbers, we said that quantum numbers are integers or half integers that describes the property of an atom. There are various types of quantum numbers. We'll be looking at 4 main types of quantum numbers. We have what we call the principal quantum number. We have the angular momentum or azimuthal quantum number, and we have magnetic quantum number and the spin quantum number. Now, when we talk about the principal quantum number, we say the principal quantum number is normally denoted by a letter small n. Okay, so when you see small letter n, it stands for the principal quantum number. So the small letter n stands for the principal quantum number. Now, the principal quantum number helps determine the energy level of an electron. and also describe the size of the orbital. So it will tell you the energy level of the electron and the size of the orbital. It can have any positive values from n greater than or equal to 1, where our n is our principal quantum number, and the n stands for our energy level or our shells. If you want to determine the number of electrons that will occupy a particular energy level, then we are going to use the formula, the 2n squared, where n denotes our energy level. Or it tells you the number of shells. So if you are within a first shell, then it will tell you the number of electrons that shell will take. If you are in a fourth shell, using this formula, it tells you the number of electrons that fourth shell will take. Now we're saying that electrons found on the N1 shell, which is the first shell, is normally having the lowest energy. And those further away from the N1. So let's take an example. If I have an electronic configuration of this nature, my N1, which is my first energy level, is called the lowest energy level. And my N2, which is my third energy level, is called the one with the highest energy level. So electrons closer to the nucleus are regarded to have lower energies. Now we said we can use the formula 2n squared to denote or to find out the number of electrons that a particular shell or energy level can occupy, where our n is our principal quantum number and n is greater than or equal to 1. So for instance, if I have n to be equal to 1, then it means that my first energy level can take a maximum of 2 electrons. If I have n to be 2, it means my second energy level can take 3 electrons in that order. The next one we want to look at is the angular momentum or the azimuthal quantum number. We said it also helps to indicate the shape of the orbital in which an electron is present. It uses the formula L equals n minus 1, where our n is our principal quantum number, which is n either is greater than or equal to 1. And our angular momentum has range of values ranging from 0, 1, 2, 3, and so on. Now we are saying if you have L to have a range of values from 0, 1, 2, 3, the 0 denotes our s orbital. The 1 denotes the p orbital, 2 denotes the d orbital, and 3 denotes the f orbital. Now, how do we do that? Let's go and look at how it is done. If I have a principal quantum number being n equal to 1, it means that wherever I see n in my angular momentum, I am going to replace that n with 1. So if I have L to be equal to n minus 1, n here is 1, so n will be equal to, so L will be equal to 1 minus 1, which will give me 0. We are saying the 0 stands for the s orbital. And the range of values for 0 is 0. The 0 does not have a range. Okay, so 0 is 0. But if I have n to be 2, I am going to have L to be equal to 2 minus 1, which gives me 1. My range of values for L is going to be 0, 1. And the orbitals will be S for the 0 and then the P for the 1. If I have n to be 3, it's going to be L equals 3 minus 1, which will give me 2. My range of L values become 0, 1, and 2. The orbitals become S, P, and D orbital. If n is 4, I'll have 4 minus 1, which will give me 3. My range of L values become 0, 1, 2, and 3. The orbitals becomes S, P, T, and F. So we are saying that is how you find the sub-levels within an angular momentum. Now let's look at the magnetic quantum number. For a magnetic quantum number, we said these quantum numbers specifies the orientation of the orbital in space. And it has range of values from minus L, 0, to plus L. So if I have L to be 1, then my range of M values become minus 1, 0, 1. If I have L to be 2, my range of M value become minus 2, minus 1, 0, 1, 2. Now, the magnetic quantum number is like a subset of our angular momentum. We are saying that when I am in an orbital where I have L to be equal to 1, I will have my orbital to be P, because the 1 denotes the P orbital. Now, in a magnetic quantum number, we are saying that if you go inside that P orbital, there are sub-levels. And we have 3 sub-levels in P. We have the Px, the Py, and the Pz. So let's take an example and see how to demonstrate this. So we're saying that if I have L, if I have N to be 1 for my principal, my L will be 0 using the formula L minus. L is equal to N minus 1. So I'll get 0, which denotes the S orbital. For the magnetic, the range of M values, there is still 0. There's no range, so I'll have S. Now, if I have 1 for my L, my range of M values, or my M, so if I have L to be 1, my M, if I have L to be 1, which denotes the P orbital, for my magnetic quantum number, I will have Px, Py, and Pz. If I have M to be 2, if I have L to be 2, which denotes the D orbital, I will have D1, D2, D3, D4 to D5. But if I have L to be 3, which denotes the F orbital, it will be from F1 to F7. Now, each of these orbitals takes a maximum of 2 electrons. So my S orbital can occupy 2 electrons. My P orbital will take a maximum of 6 electrons, 2 electrons each. My D orbital will take a maximum of 10 electrons, 2 electrons in each of the orbital. While the F will take 14, 2 electrons from F1, F2 to F7. Now, when we talk about the spin, we said for a spin quantum number, this describes the spin of an electron. So it is normally, so when we write out the electronic configuration for atoms, we denote the number of electrons on an orbital with a spin. So if I have 2 spins, it means I have 2 electrons on that particular orbital. If I have a single spin, I have 1 electron on that particular orbital. We are saying when you are writing the spins, they must be opposite. So one spin stands upright, the other spin will be inverted. You don't have spins standing in this form. No. Neither should you have your spins in this form. No. One must stand up, then the next spin must be inverted. So that is the spin. Now, let's talk about orbitals, which we've mentioned earlier. When we talk about an orbital, it's just a region or a space around the nucleus in which the likelihood of you finding an electron is very high. So, any space around the nucleus that the likelihood of finding an electron is very high is known as an orbital. Now, we are talking about the S orbital. We said the S orbital have what we call a spherical shape. And it is the orbital with the lowest energy. And it occupies a maximum of 2 electrons. So when you are writing an electronic configuration and you are in an S orbital, you must assign it 2 electrons. The next is the P orbital. We said the P orbital have a dumbbell shape. and the maximum electrons it occupies are 6. Px takes 2, Py will take 2, Pz will also take 2. And the next is the d orbital. It takes a maximum of 10 electrons. It has 5 orbitals, d1 to d5, and it's regarded to be a higher energy level than the p and the s. And the highest of them all is the f orbital, which has 14 electrons, with in the f1 to the f7 orbitals. We want to see how we can assign electrons on an orbital when writing out an electronic configuration. We said to do that, you can use what we call a flow chart. This flow chart allows you to tell the flow of the electrons within the orbitals. So let's see how it's done. We said the N stands for our energy level or our shells. On your periodic table, you have N1 to N7. We have 7 numbered periods on the periodic table. Now, the energy level of these orbitals is from S is the weakest, P has a stronger energy level than the S, D has a stronger energy level than the P, F has a stronger energy level than D, P, S. So when you are sharing electrons or you are distributing electrons, you enter into lower energies then before you think about entering into higher energies. And for us to do that, we are using what we call a flow chart. If I enter into N1, I'll use the formula L equals N minus 1. So L will equal to 1 minus 1, which denotes 0, which stands for the S orbital. So that means that in my first energy level, I will only have the 1s orbital there. If I have L to be 2, I have 2 minus 1, which will give me 1. The range of values will be 0 and 1. So the orbitals will be S and P. So in my second energy level, I'm going to have a 2s and a 2p. If I move to the third energy level in that order, it will be 3 minus 1, which will give me 2. The range of values becomes 0, 1, and 2, which is the S, P, and the D orbital. So I'll have 3s, 3p, 3d. Then I'll continue to 4s, 4p, 4d, and then 4f. Now we are saying that the maximum orbitals we are going to look at is from the S, P, D, and F. So from the 4th energy level to the 7th energy level, we will end our orbitals on the F. So this becomes 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s, 7p, 7d, and 7f. Now, we are going to indicate the flow of the electrons diagonally. So I'm going to draw an arrow from the S orbital, 1s down, then I'll come to 2s down, then I'll go to 2p, then cross through to 3s, from 3p cross through to 4s, from 3d cross through to 5s, in that order. You cross it out diagonally. Now this tells you the flow of your electrons. Now these electron flow, we said they move in what we call a zigzag or a snake-like manner. So if you are writing an electronic configuration, when you enter an s orbital, you are going to go to the next orbital, which is your 2s. From a 2s, we go to a 2p. From a 2p, we go to a 3p. From a 3p, we go to a 3d. We move in that snake-like manner. Note, never enter into an orbital through the arrow, the pointed edge. Okay, so we are entering through the back of the arrow, not through the pointed edge. If you use the pointed edge as your snake-like movement, your configuration would be wrong. So let's take an example. If I was asked to write the electronic configuration for magnesium, I will enter a 1s orbital. So I'll give it 2 electrons. The next is a 2s. I'll give it 2 electrons. This becomes the electronic configuration using our flowchart. Now let's see the electron in a box method. When we talk about an electron in a box method, we are basically talking about using boxes and spins to denote our electrons. So when we draw a box for a particular orbital, then we indicate the number of electrons by a spin in the box. That is all about the electron in a box method. We'll apply it later on during the configuration of some elements. But let's continue and look at, there are certain gentlemen that help out with the electronic configuration. And we are going to look at the WASSCE principle. WASSCE states that if you are within an energy level or you are within an orbital and you are sharing electrons, that you should enter into orbitals with lower energy. And when you enter into orbitals with lower energy, you should fill them first. And when you are filling, you must fill them in full before you think about filling orbitals with higher energies. So if that is the case, if we are writing out the electronic configuration for carbon, we are going to enter a 1s orbital. We'll fill it in full. Move to a 2s orbital. Fill it in full. Then we move to a 2p orbital. If we are to write for nitrogen, we'll enter a 1s2, a 2s2, a 2p3. That is the electronic configuration or the rule according to WASSCE, that when you are entering a lower energy, ensure that lower energy is felt out in full before you think about going to the next energy. Now note, when writing the electronic configuration for an atom, the electrons are written on top of the orbital, not in this form. If you write it in 1s2 where it is in this form, or you write it as a subscript, your configuration is wrong. It must be on top of your orbital. Good. So if you are writing an electronic configuration for aluminium, according to WASSCE, we enter a 1s2, a 2s2, a 2p6, a 3s2, and a 3p1. Now the next rule is the Hands rule. It states that when assigning electrons in an orbital, each electron will first fill all the orbitals with similar energies before pairing with another electron in a half-filled orbital. What Hans is saying is that when you are distributing electrons, he is not disputing the fact that WASSCE says that fill orbitals with lower energies first, but he's adding up to that principle. He says that when you are filling orbitals with lower energies and you end up entering into an orbital that contains a sub-level, like a p orbital, that has a px, py, pz, that when you are sharing the electrons within those sub-levels, don't give them two electrons throughout. First of all, start giving them 1 electron each. When you give them 1 electron and you realize that you have more electrons, then you come and pair with a half-filled orbital or half electrons. But don't go ahead and share the 2 electrons. You will get to a point whereby some of the orbitals may not get. So for that reason, always give them 1 electron each. Then you come back and pair with another electron. In the Pauline's exclusive principle, it states that no 2 electrons can have the same set of 4 quantum number. What it simply means is that you cannot give an orbital more than 2 electrons. The maximum electrons an orbital can take should be 2 or less than 2. But you cannot assign an orbital 3 electrons. You would have violated the Pauline's exclusive principle. And that when you give an orbital an electron, be it 2 or 1, you must assign or you must accompany it with what? A spin. So that brings us to the electron in the box method. So you draw some boxes beneath your orbitals, then you assign the spins in the form of what? The electrons you distributed. So if you have 1 electron, you indicate a single spin. If you have 2 electrons, you indicate double spins, and they must be opposite. So let's take an example. So we have magnesium. So we will assign the spins for this electronic configuration. Basically, this is how the electronic configuration works. I hope you understood If there's something you did not understand, please don't hesitate to leave your question in the comment section.